Good day, folks. In today's class, I'll be talking about the new topic that is center limit theorem, also known as CLT. Now, I'm going to start here with some basics which we've done in chapter number 7. So we talked about that anything which follows a normal distribution, so normal distribution like this, we can simplify that those questions with the help of this formula Z equal to x, well, not x bar, it is x minus mu divided by sigma. So x values are represented on this side, and z values are represented on this axis, and then the probability values are represented in the middle. Starting from 0 goes up to 100%, or you can also call it as up to 1 for the probability value. Z score goes minus 3.6 to positive 3.6 on the right hand side, and here the mean value, and here whatever the x value correspond to that mean value is. So that's what we did in chapter number 7. And one thing you might have noticed, I was always following the normal distribution. Now, if any value which follows the normal distribution graph, only then I can apply this formula. If it is not following the normal distribution, then I cannot apply this formula to the accuracy. So what to do in that scenario? So for example, if you are given something like this negatively skewed graph, or something like a positively skewed graph. So sometimes the distribution also follows this positively or negatively skewed graphs also. So now in this case, I'll take a practical example of this one. So for example, if I talk about people falling sick, so naturally what happens is people gonna fall sick when they are in the later stages of their life. So I'm gonna say randomly, in a city, a survey was conducted where they were asked that what was the first time in their life when they were hospitalized. So not that I'm not saying that the young people cannot be hospitalized, but the overall percentage or overall chances of a young person going to the hospital is far less compared to an old person. Now, let's say I collected a sample of 1,000 peoples here, 1,000 people, and now in this 1,000 people, someone said well they were 5 when they first time had to hospitalize. Someone said maybe 10. Someone said then 15. Then maybe someone said 18. Then someone 25. Then 35, so and so forth. And we kept on calculating the data, and later on majority of the people said after the age of 60 they were hospitalized. So 61, 62, 63 up to the age of 100. Okay, so this was the data which I collected, and now when I try to put it under the normal distribution, I can clearly see there was a skewness, that majority of the people, when they were hospitalized in their later half of their life. And let's say for this section, the mean came out to be 65 years. Oops, what happened here? I accidentally opened another page. So 65 years is when people were hospitalized on an average. All right, so the mean value will be somewhere here. This is the mean value for people falling sick. Now, as I said, I cannot apply all the z value rules on this one, which is x minus mu divided by sigma. I cannot apply this formula. So now in this scenario, what we're going to do is, if I start taking the samples out of this huge population, I'm going to call this a population of 1,000 people, which was under the observation. Now, if I start taking the samples of, let's say, uh, 40 people, so a random sample of 40 people, and I picked up again someone with the 5, then 20, then 27, 30, 35, and then the average age came out to be, let's say here, 55 years. And then another sample I collected, the average age came out to be 65 years. Again, I'm making a samples, these samples of 40 from this population of 1,000, and one value can be repeated multiple number of times. So if I took the 5 years here, I can also take 5 years here also. Okay, but that will be that the other terms will be different. Like For example, I can take 5, 20, 27, but rather than taking 35, someone with the 45, 47. Another sample can be 5, 20. Now another age can be 30, 35. So this way I started collecting a lot of samples, and I started getting the averages from those samples also. So let's say this average was 65, another average came out to be 35, another average came out to be 59, another average came out to be 74, another average of 40 sample came out to be 85, so and so forth. When I started collecting the samples, so I can see that I have a complete new data set, this complete new data set of the means of the samples. Okay, so these are this is a mean of a sample, this is another mean of a sample, another mean of a sample, so x bar. So this is a mean of the sample. Now, it has been observed that the mean values, once you're going to try and put it under the normal distribution graph, you will find that the mean of this means, if I now take the mean of these means, that value will come approximately same as the mean of the actual population. So again, one more time, I'll say mean of the means. Okay, so what are the means? So these are the mean. This is x bar 1, x bar 2, x bar 3, and so forth. When I'm gonna take the mean, again a mean of all these means, that mean will be approximately same as the mean of the population. The mean of the population was 65 in the given uh, in a given population of 1,000. Okay, so now what we can do is, because these means are same, so I can draw it under the normal distribution graph. So this will be 65, and here the x bars are here, so some x bars are less, some x bars are more than 65. But if I take the average, that come out to be the 65, which is same as the mean of the population. So hopefully you are able to understand what center limit theorem is. Now the formula to calculate the values now will be z equal to x bar minus mean divided by standard error, sigma x bar. And standard error is equal to, this value is equal to sigma upon square root of n. N is the sample size, sample size. Okay, and this value mean, this mean is equal to the mean of the samples. So the both the mean of the population is same as the mean of the sample means. So this is the formula we're gonna use to solve the problem. So that was about the center limit theorem, and I'll see you guys with another video. Till then, goodbye.